I'm going to talk about putting vacant buildings to sleep. And this is actually reporting results from the work of a lot of people. First, of course, I need to acknowledge and truly thank the University California Office of the President for the Carbon Neutrality Initiative and their support, but also Department of Energy and EPA and the California Energy Commission, who have in various ways contributed to this effort. And the most important thing are the students who've participated, namely Lisa Slaughter, Alex Sloan, Sadia Gul, Sam Reddy, and people at UC, Josh Moorjohn, Nico Fauché-Magnan, and then at Lawrence Berkeley Lab, we've got John Elliott and Chen Hong. And all of these people have been participating in ways which I think you'll see as we go along. So let's get started. What is putting vacant buildings to sleep? What it's about? Here's my plan. I'm going to talk about how I got to here. It's sort of a personal history. And then some of sleeping buildings research that's being done, has been done at UC Davis, although I draw upon other places too. And then finally, how the world's changed since this project started and how we're going to need to pivot and keep this project relevant. So way back almost 20 years ago, I became fascinated, maybe even obsessed with the fact that a lot of appliances were consuming electricity while they were switched off and or not performing their primary function. And this was called standby electricity. And I spent a lot of time on that. I was the one who more or less pointed out that 5 to 10% of the electricity used in homes went to standby power consumption of a whole host of appliances, some of which I've displayed there from a 2001 PowerPoint. And that when you put that all together around the world, it represented about 1% of the world's carbon emissions. And one of the chief culprits was what they called vampires. That's the thing on the right. These are these little devices. And here's a fun fact that those are the external power supplies that got their name because they have 2 teeth and they supposedly suck electricity throughout the night. I've been blamed for that term, but it's not me. Somebody else made it up. Anyway, these devices have been are around still. There's lots of standby power, but although we've been incredibly successful in reducing the electricity use per product since then, in some cases we've reduced it as much as 90%. I like to say we won the battle, but we lost the war, because even though the per product consumption has dropped enormously, the number of components with standby power has increased enormously. So we're probably still at the 5 to 10% of residential electricity use and 1% of global carbon emissions, even after 20 years. I more or less strayed from this topic for a while, and then I began to come back to it in a way, because I realized that there was another situation where building energy use had some features that were very similar to that found in these appliances. And let me give you some examples about that. In the residential area, if you look at your electricity consumption at 3 a.m. in the morning, you can do that with your own smart meter. You'll find, surprisingly, that your electricity consumption is high and not that much lower than during the daytime. And in fact, if you look at a large collection of homes in California, as Marian Borgeson did, she found that the electricity use of homes, if you looked at them, about 40% of the electricity consumption was constant loads. That is to say, the fraction of annual energy use that occurred as a constant load was 40%. So that even in the middle of the night, the electricity consumption didn't drop very much in homes. Well, I began to look at that, and then somehow I switched over to commercial buildings and realized that, you know, the situation was probably worse in commercial buildings. And here is a rather difficult to interpret daily load profile from a building at Lawrence Berkeley Laboratory if under two days actually, and you follow the black line and you can see it increases during the daytime in both in a normal day and then with a demand response event, and then it comes down again. And it looks, oh, that's interesting. But to me, that wasn't the important part. It was the fact that the base load consumption, the constant load, was 5 kilowatts, and that in the end represented about 60% of the building's electricity consumption, and that maybe we were focusing on the wrong aspect of these buildings, that there is this constant or continuous load that we needed to deal with. Well, then I started asking myself, well, maybe we should look at what might be more easily savable, and that was the electricity consumption, and maybe that constant electricity consumption when nobody was in them. Well, why should we focus on those? Because in many of these buildings, and especially at places like UC Davis and Lawrence Berkeley Lab, the number of hours in which they are vacant actually exceeds the number of hours at which they are occupied. And by vacant, I mean those nights, the weekends, vacations, and holidays, and also pandemics. Another reason you might want to focus on the time when nobody's in them is because there are no occupants to complain if you take some conservation measures. And if you know that nobody's in them, if you're absolutely certain that these buildings are vacant, then you might be able to take some more aggressive measures than would be possible under ordinary circumstances. And then because of this unique situation of them being vacant with 0 people in them, then there might be some new strategies or new approaches that might be unique to vacant buildings. And maybe when we learn about how buildings use energy when nobody's there, we might also apply some of those lessons to when they are occupied and eliminate some waste too. Okay, well, ideally what we have is a situation with buildings so that there is some sort of relationship that the more occupied, the more heavily occupied they are, when the occupancy level increases from vacant to occupied, the energy consumption will increase. And this would be the theoretical kind of relationship. Well, you know, here's the reality. When we look at a lot of the buildings at UC Davis, we look at many office buildings, and often even our homes, the reality is that even when the buildings are near empty, they're using 70 to 90% of the electricity consumption. And in fact, my own office at Lawrence Berkeley Laboratory actually increased its energy consumption during the pandemic. And that's another story, but it's still important to realize that there can be these perverse examples too. So what we really want to do, and this is our research focus, is how do we restore some sort of relationship between the occupancy level of a building and its power consumption. Here is a further example of how off kilter this relationship is. If you look at the ratio of vacant power to occupied power at UC Davis, you first of all will see in this bar chart that there are some buildings like laboratories where the electricity consumption is virtually constant regardless of how many people are in the building. But those are laboratories. Yet if you look then further down this list on buildings that are not laboratories, and we are confident that they are truly empty and nothing is going on in those buildings, we still see very large ratios of vacant power to occupied power. So we wanted to study that a little bit. But before one of the first steps in that analysis was shown during the pandemic in Davis, where we were able to, where where you could see there was a 90% reduction in occupancy, but electricity consumption fell only 15%. And the reason we know the occupancy fell, besides the buildings being locked and the students were told to go home and the staff were told to go home, is we looked at the Wi-Fi connections. And we could see over very quickly during the beginning of the pandemic, the blue line, those are the Wi-Fi connections over the whole campus. And you can see it went almost to zero during fairly quickly. But if you look at the electricity consumption, it barely fell, 15%. Steam and chilled water, it's another story, but I'm focusing just on electricity now. So what's going on here? Why didn't electricity consumption fall as much as occupancy? In this case, in order to understand that, we studied some buildings, and Geet Hall was one of those. And it's a lecture hall with classrooms, but not much else in it. We thought that would be an easy building. And we then looked at the Wi-Fi connections and the energy consumption in that building. The blue is the electricity consumption. And the way Geet Hall works is it's supplied with heating and cooling centrally. So this is really just the electricity consumption for stuff that's going on in the building. And then we looked at the Wi-Fi connections, and that's the orange, and you can see how they fluctuate. And then we had a break for a spring break, and nobody was in the building. So there were 0 Wi-Fi connections, but electricity consumption just plodded along at 5 to 10 kilowatts. Another reason we know that that there is a lot going on, a lot of consumption going on in the building that wasn't related to HVAC is the facilities department did a little experiment for a few days, and they shut down the HVAC system. And you can see that even though the HVAC system was shut down in Geet Hall, the consumption was still very high. So what's on? The answer to the question is fairly obvious in retrospect. It's what we call the miscellaneous electrical loads. The acronym that seems to be most popular now is MELS, but we also hear plug loads and other residual electricity use, all sorts of different names. I happen to like miscellaneous electrical loads. Various studies have suggested that these MELS are responsible for about 1/3 of electricity use in buildings, and there are projections that it will go up to 50% in modern buildings. What are those MELS? Here's a short list, and you can see that some of them are familiar. Some of them might not be. You might not think about elevators as an example of MELS, but that or vacuum pumps, hot water circulation pumps, but more than anything, it's computers and network equipment and a lot of electronics that we find in buildings. Well, then we wanted to look at what went on in Geet Hall to see what sorts of MELS were responsible in Geet Hall. And thanks to a study by Alex Sloan, we did an audit and estimated that the electricity consumption during the nighttime when 0 people were present was something like this. And you could see that audio video equipment was very large, and network equipment, or at least the network equipment room, represented another very large slice of the electricity. And so we started doing a survey, this is what on the left is one of the audio-visual racks that you would discover in a lecture room in UC Davis. You might find slightly smaller ones in the smaller classrooms, but this is typical of what you would see in a lecture room. And in the middle is an infrared photograph of it. It's hot, and that's a photograph taken when nobody was there and that it's actually nobody was using the classroom. And that you'll see if you go in the back and various other parts of the of the racks and the systems, you'll find lots and lots of things plugged in. So we started studying the AV equipment because that was clearly an important point. We've soon found, and just to convince ourselves, that the electricity consumption of the AV equipment did not change very much. Here you can see it's about 300 watts, 325 watts. And this red area was when the university was shut down during the wildfires. And well, the university may have been shut down, but not the AV racks. They were just chugging along, drawing the same amount of power as ever. Furthermore, as we started doing more examinations of these audio-video racks, we discovered there are several generations at UC Davis, and this applies to almost all the university campuses. And the curious thing is, the newer the generations, two things happened. They began to use more and more power here. From 100 watts, it's going up to 680 watts in the most recent ones. And the other thing is, when they were switched off and not being used, they continued to use much more power. So it went down. Originally, they would go down to about 60% of their full load. And then the latest generations are about 90% of full load. So that's obviously an area for further study. And so we're trying to understand what is using the electricity. And we learned that there are lots of components in those racks, but curiously, only a few of them are used by most lecturers. More important from an energy perspective is that only a couple of them are able to go to sleep on their own. So these things tend to just be operating at on mode all the time. And the other thing we learned, of course, is that while it may be easy to pull the plug on the whole device, it may be more challenging to plug it back in and be confident that everything else will successfully reboot. So that I say that switching on is more challenging than switching off. And for that reason, the IT department strongly discourages switching off the racks. In fact, they make it impossible to pull the plug on them. They actually have it set up so they are essentially hardwired. And they do that partly because of the fears that the devices will not successfully reboot. They think there might be some lifetime problems for the restarting. And I think overall, the biggest issue is no incentives. Their goal is to have no complaints. And so the best way to have no complaints is to make sure that they're on all the time. So as a research area, we need to figure out how the audio-visual racks and other complicated systems like this can be reliably switched off and then with confidence switched back on again when needed. Now, if you go back here, one of the other points was the network equipment room, in that yellow one. Here is an example of the kind of device that you'll find in some network equipment room. This is an Ethernet switch and the power consumption of an Ethernet switch under different loads or utilizations. And you can see that the consumption drops from 100%, it's using about 376 watts, and at 0%, it's using 367 watts. And that's a reduction of all of 3%. So that even though the utilization of it falls about falls 100%, the power consumption falls only 3%. And this kind of situation is increasingly common among these network equipment and various other kinds of electronics. Routers, Wi-Fi routers is another example. And this is something that we need to figure out how to fix. And there are solutions to that, and we just need to get them out there and to meet the reliability requirements that we expect in IT equipment. So we wanted to save energy in these buildings during their vacant periods, and so we needed a strategy. And our strategy consisted of three steps that we would imagine in the future we could employ. One was we needed a procedure to determine when a building was vacant. And once it was vacant, then we needed to signal to all this kinds of equipment, these MELs, that this building is vacant. You can enter a vacancy mode because nobody needs your services right now. And then when somebody enters the building, you've got to signal to them that it's okay to wake up now because somebody's in the building. In fact, it's not even okay. You've got to wake up. So the first issue is inferring vacancy. And we developed, we learned a lot in this because one of the first realizations is that vacancy and occupancy are very different animals. Because occupancy is something that basically goes from 0 to many, many people. And it may be only, but whereas the vacancy is binary. Either the building is vacant or it's not. And furthermore, from a controls perspective, occupancy is something that can be sensed. You can put in all sorts of different occupancy sensors, but vacancy is well, vacancy doesn't have, there are no vacancy sensors. So what in fact you need to do is you need to infer vacancy from various other sensors. And so it's a very different concept to sense occupancy but infer vacancy. So what we needed to do was to create a vacancy inference engine. And that vacancy inference engine's job was to estimate the probability or the confidence that the building is vacant and use that signal, broadcast that signal to all the MELs. And this became and still is a major undertaking, which Lisa Slaughter has been contributing to and wrote her thesis about. It employs a technique of sensor fusion which combines information from many different kinds of sensors to calculate a probability of vacancy. So let me just show you briefly how that vacancy inference platform would work. It draws upon data from a variety of sensors, such shown there. Then there is an engine that combines this information. It uses principles of sensor fusion to then come up with a % likelihood that the building is vacant, and then it broadcasts that information in the form of a vacancy signal to all of the MELs that can receive that and to receive that signal and then go into what we would call a vacancy mode, a lower power consumption than they would ordinarily be in if they didn't know the building was vacant. Well, this is much more complicated though than it looks, because it requires significant modifications to the equipment, because most devices today don't have a vacancy mode, and so we need to figure out ways to have a new vacancy mode built into these MELs. And not only that, we need to have a way for those MELs to receive the signal, and so more and more those MELs will need to have a communications capability to receive that signal and perhaps some other signals, such as dealing with the grid status. But for a few devices, we're nearly there, and we probably can already implement some of this, at least in a prototype form. But in many other devices, such as a hot water recirculation pump, we're going to need to figure out how to do retrofits or wait until that device gets replaced with a new circulation pump. Well, So now we get to the real problem, which is the pandemic um, pivot. What has happened now is that thanks to the pandemic, maybe vacant buildings is a problem right now, but the future may be slightly different, and it may in fact influence the direction which our research will go. We're going to go to we can imagine in the future that buildings will not only be perhaps vacant more, but the real situation will be that the vacancy levels will fluctuate much more. And so we need to make buildings much more dynamic and responsive to the level of occupancy, and in order to make sure that we are not wasting energy. So the new task will be achieving efficient performance over a much wider range of occupancies than the existing buildings are designed or managed today. And so that, I think, will be part of the aspects for the future work at UC Davis. Here as we move forward, we're going to do two things. We're going to first identify times when the buildings are truly vacant and continue working there, and then also ask ourselves, how can we apply some of those concepts to buildings when they're not vacant but less occupied at lower levels. So some of the questions that we're going to be asking is what kind of first of all, how much energy can be saved? So we're going to be visiting buildings in Davis and auditing them to find out again what's really consuming that energy during those unoccupied periods. What mills can we find that are responsible for the high energy consumption, similar to that which we saw in Geet Hall? And then, and we know some of those. For example, if you visit some of these buildings, you will see that that there are classrooms still full of monitors and computers fully on and consuming power, even though nobody has visited those computers for literally months. But there is a lot of equipment that is less obvious, hidden, such as pumps and fans and other kinds of equipment, such as little electric water heaters. All of these are the mills that add up to the vacant energy consumption. Well, once we know what those are, we'll try some experiments and manually place all of those devices into something like a vacancy mode. To be sure, we can't really make them go into a vacancy mode because they don't necessarily exist, but we can kind of simulate what it would be like. And then we can observe the energy savings. So we can get some confidence of how much of that vacant energy consumption can actually be saved. At the same time, we're going to be improving the vacancy inference engine, because while we've got the concept down, it's in fact draws upon a lot of complex data from many different places. And sensor fusion is still an emerging field, especially in the way that we're applying it. So we expect that we'll need to further modify and improve it, eventually transferring it to the facilities office so that it can be used to alert facilities office to which buildings are vacant, and then ultimately to controlled equipment that can be switched into vacancy mode. At the same time, a parallel path of research will be to examine individual pieces of equipment and ask ourselves, how can they be redesigned to reduce their energy consumption? And some of these examples is, of course, of the AV equipment, but also the network devices and more mechanical devices like pumps and water heaters. So I've talked almost nonstop, and partly because I wanted to leave lots of time for questions, but that means that I can just list the conclusions and begin asking questions. As you can see from this description of the building performance, for the most part, the energy consumption of buildings has been decoupled from the amount of services they provide. We know that one of the reasons for this decoupling is that the electricity use from MELs, and that we need to figure out a way to recouple the electricity, the occupancy levels, and the MELs services. And those are going to require new strategies, and it will, I believe, draw upon novel applications of sensing, controlling, and the design of equipment. So with that, I've literally sprinted through this presentation, but I have a feeling, given the fact that there are over 75 people listening, we're going to have lots of questions, and I wanted to leave time for you to ask them and make suggestions too. So thank you very much.
Great, thanks so much, Alan. Yeah, so if you have a question, go ahead and either raise your hand or put your name in the chat box, and we'll go ahead and wait just a second, and hopefully we have some questions coming in. And I see a number of your students, Alan. I see Lisa's here, and Alex and Sadia are all listening, so that's great.
And they, of course, are welcome to clarify and contradict me.
Well, I know I always would bump into Lisa analyzing video, so I know she spent many hours doing that to look at vacancy. Oh, I see a question here. Paul, I'll go ahead and unmute you. All right, you should be unmuted, Paul.
Hey, Alan, Paul Ehrlich, how are you today?
Oh, thank you. Hi, Paul.
Alan, the question I had is, did you find that the non-MELS loads like HVAC and lighting had the building operations staff gone to the effort to make sure that those were shut off, or did they continue to run on their normal mode where they were operating during the day and shutting off at night, even when the campus was shut down?
I think it depended upon the specific device, but a lot of the MELs are uncontrolled. On the other hand, the HVAC equipment, most of the HVAC equipment and some of the lighting are controlled. And I think the facilities department has managed to deal with the HVAC and some of the controlled lighting. But so far, there's been a limited attempt to switch off devices manually.
Okay, thank you.
But I'm willing to be contradicted there, because I know there are probably several people from the facilities and the Energy Conservation Office who will say, no, we've gone through certain buildings and taken measures to switch things off.
Great. Okay, we have another question here from Vince. So Vince, if you have, some folks don't have audio, but if you do, I'll go ahead and unmute you. All right, Vince, you are unmuted.
Can you hear me?
Yep.
Sure can.
Sweet, right on. Well, how's it going? Thank you so much for your time. This has been really informative, and it's an interesting situation. But my question is that I've never thought to use network data, so number of users on a network, as an indication of occupancy, and that's really slick. But I'm just trying to wrap my head around how we would ask a customer to identify that and track that, so that we could also, use that as real time, or as a certain trend set of occupancy data. So I'm curious how you did that with UC Davis, and how I might, as an energy auditor myself, ask a customer to set something like that up to track the number of users. Does that make sense?
Absolutely. And in fact, we at UC Davis and Lawrence Berkeley National Lab have developed many techniques to capture this data. It's relatively easy now if you have cooperation of your IT department, and it does not violate any personal privacy issues. It's all anonymous. It's simply the number of connections, and so it can be logged remarkably easily. And as you can see right there, you can see that it was UC Davis is able to do it for the entire campus. And so we can collect that data literally from a whole campus to a building, and even of course to your own house if you have if you're the administrator on your Wi-Fi router.
That's pretty slick. Is there any chance you guys have like just like a fact sheet for what you would need in order to set something like that up? Because yeah, I can see how the immediate hurdle would be getting approval from a customer's IT group, assuming I'm not with that company. And so it'd be great just to have a resource to say, hey, this is a technique we could use. It's non-invasive, just to reassure folks that hey, we're doing this for a good cause and it's not coming across as shady. Curious if there's anything that I might be able to use when I'm having conversations with customers.
I'm not familiar with it, but I think it's a great idea, and I think we should make sure that at a minimum, every campus at UC campus is familiar with it, and we should make such a document available to other groups as if it's useful.
That'd be really cool.
Well, thank you very much for that suggestion. Yeah.
All right, thanks, Vince. Okay, we have a question from Josh. So Josh, I will go ahead and unmute you here. Okay, Josh, go ahead and ask your question.
Thank you. Alan, just quickly, you had some interesting ratios. Were those all comparing April of 2020 to April of 2019 for the building ratios?
I think let me make sure we're at the right place. Were you thinking of this one?
Yes.
These were taken. No, I think they were taken about a year and a half ago. It was not done during any specific period, except that we were able to be reasonably confident that we were isolating occupied and vacant periods.
Okay, and I guess the reason I was wondering is because California has kind of a unique climate that may not have as much HVAC as other parts of the country, and so I was trying to think of how this, whether or not this applies to other parts of the country, or if you would see something different in places that have more cooling or heating loads.
Yeah, that's a very good point. And remember, these are university buildings on a central heating and cooling system, and so the HVAC has been mostly removed from this comparison, and so I guess you have to generalize with caution. And thank you for calling attention to that.
All right, we have another question from Tim Clark. So I'll go ahead and unmute you, Tim. Give me a second to scroll down. Here we go. All right, Tim, go ahead and ask your question.
Yes, I was just curious if you had been able to review the effectiveness of any of the plug load reduction devices that are on the market today, ones that use schedules to put devices to sleep.
Thank you for your question. You were curious about the different kinds of plug load management system technologies that are available, and personally, I'm not a fan of those. Sometimes you can get fairly significant savings initially, but over time people get annoyed and they unplug them, or they simply don't remember to use them, and so that the savings tend to diminish over time. I'm an advocate of trying to get that intelligence into the device itself, rather than into the rather than to put it into a plug load controller. They work sometimes, but not. It's not something that I would advocate.
Good, thank you very much.
Great, and we have a question from Daniel Simpson. So Daniel, I'll go ahead and unmute you here. Here we go. All right, Daniel, should be unmuted.
Thank you. So I had a question about the resistance to powering down racks, like the AV racks, the issues with rebooting and reliability. And I was wondering if there were any studies that have been done showing what sort of problems like those are causing, or is it just an inferred, like if we don't need to cause problems, are we just holding back? And if you know of any studies that have been done, or if you're planning to do any.
Thank you. Your question kind of illustrates our dilemma. We couldn't find any studies about the energy use of AV equipment, or and especially the racks, and then also some careful studies of the problems of shutting them down and rebooting. But there's a lot of anecdotes. There are a lot of I think horror stories that the IT staffs will tell you, and they should be taken seriously, because remember, their job is to make sure that when a lecturer goes into the classroom, the system is immediately operating, and the last thing they want to do is have a complaint. So they have evolved various methods to minimize their complaints. Unfortunately, those don't necessarily result in efficient operation. I hope I answered your question there. The short answer is no, there isn't any.
Yeah, I mean, I'm just thinking about where we meet, the reliability standards and the need to reduce it. I mean, if AV equipment is running, 33% of the load of a building when it's completely unoccupied, it seems excessive.
I agree, but to some extent, I cherry picked there. This building turned out is almost exclusively classrooms and lecture halls, so it's not so surprising that the AV equipment is a significant part of the electricity consumption. But what's, I think, most revealing is that it's a huge part when nobody's there too.
Thank you.
All right, and we have, thanks Dan, we have another question here from Lindsey Baker. So Lindsey, I'll go ahead and unmute you.
Okay.
There we go. You should be unmuted, Lindsey.
Okay, hi, thanks so much for this. This is really helpful and amazing. I'm just wondering if you can talk a little bit more about vacancy and occupancy sensing in terms of the types of options that people have. You mentioned this in an earlier question that was just asked, but in particular, thinking about portfolios where they may not have all of the options available to them for occupancy and vacancy sensing. Are there technologies that you think are, or methods that you think are more helpful versus less helpful, et cetera?
I hope I understand your question correctly. I'm going to rephrase it. In buildings where they are less sensor rich, how can we detect vacancy and perhaps figure out ways to turn off equipment while nobody is in the building? Is that?
Yeah, that's a pretty good one. I'm just sort of thinking about baby steps on the way towards better occupancy and vacancy sensing, and so that would be a very helpful way to
So the most important thing that can be done is to make sure that the electronics and devices that have sleep modes can actually switch into them, and that they have not been in some way disabled. And so that requires some research and investigation in your own buildings to find out, are my PCs going to sleep? Are the displays going to sleep? Are the printers going to sleep? And ensuring that that actually happens. Increasingly, we will find equipment that goes into a sleep mode after periods of no occupancy, and we just have to ensure that at a minimum that those devices are allowed to do that. Beyond that, there's really not too much you can do that is not labor intensive. And by labor intensive, I mean visiting the water heater, the electric water heaters that may be present, and lowering, setting them to a lower temperature, or turning off your refrigerated drinking fountains and things like this, all of which require enormous amounts of time, not only to switch them off, but then also to switch them on again, and remembering to switch them on again. And for that reason, it's not easy.
All right, we have another question coming in from Brian, and Brian has a question related to HVAC, and he may have attended our webinar that Teresa gave, talking about schools and how to prepare them for reopening, especially with COVID. So he has a question kind of related to that. Go ahead, Brian, you should be unmuted.
All right, hey Alan. Yeah, so I'm interested in how will HVAC energy usage compare to the occupancy? Because I know you bring in fresh air, you have to condition it, that increases your power use, and so I'm not surprised that the labs had pretty constant use. When we were talking about schools, we were talking about bringing in more fresh air per person, and also bringing in fresh air a few hours before occupancy, whereas most systems that I work on day to day run on recirc as they reach set point. How is all this going to affect the energy consumption per capita?
That's a very good question. And I think there's a lot of discussion right now, and you've basically pinpointed some of the dilemmas that for the dealing with the pandemic. People want to do two things. They want to reduce the number of people in the building. At the same time, they want to increase the ventilation. And how will that affect energy consumption? I guess what I want to do is say I think that's something that needs further research and work, but I'm focusing on other aspects of the building which I don't think are so directly related to the pandemic and viral loading and exposure. So what I guess what I'm trying to say is I'd like to dodge your question and say that I'm focusing on the MELS aspect rather than the very important aspect of sufficient ventilation in these buildings. I know that's not a satisfying answer, but I think there are other people who can probably give you more information on it than I can. Okay.
Thanks, Alan. Okay, and we have another final question about whether you have any information on plug load use from campus during this current shutdown.
I'm sorry, could you repeat the question?
Sure, whether you have any information on plug load use during the current shutdown with COVID-19.
At UC Davis?
Yes.
So I mean, the only thing we really have is this information from UC Davis over for the whole campus, and then of course for individual buildings, but that electricity consumption fell about 15%. And so presumably most of the appliances in the buildings and the MELs are continuing to operate as they always have. And there's been no great change. However, I think now several parts of the campus are recognizing that they need to address it because people are not coming back immediately. And so it may become worthwhile to do these manual visits and either switch off or switch down these MELs.
Great. Okay, well, we got a couple of requests for a PDF copy of your slides. So if that's okay with you, we can share that with folks. And then the webinar video will be available, of course, in a day or two on our YouTube channel. And then I'm going to go ahead, if it's okay, Alan, and share your UC Davis email if people want to follow up with you.
Of course.
Okay, so I'm going to chat that out to folks. And then if there are any final questions, oh, wait, we have a couple more. So Caesar, let me go ahead and unmute you. You can go ahead and ask a question. Here we go. All right, Caesar, you should be unmuted.
Yeah, when a particular building is declared vacant, are there university guidelines that need to be followed, such as equipment shutdown?
I'm sorry, I didn't understand your question. Could you repeat it?
When a particular building is declared vacant, are there university guidelines that need to be followed, such as equipment shutdown? Because, you know, is there a formal declaration that a building is shut down, or how do we know?
No, there is no formal declaration that a building is vacant. And this may be, we have to be careful about this word because it could be confused. When I say vacant, I really mean it's just unoccupied. But it's only for a brief period. It may, well, usually it's only for a brief period, for a week, for a night or a weekend or something like that. The pandemic is an extreme case where the buildings we know are unoccupied for large periods of time. Although there may be occasional visits by a custodian or the security services or something else, but essentially the buildings are unoccupied, and there's no formal declaration of that. Beyond perhaps locking the doors so that the only people who can get in are the ones who have official access privileges.
So it seems to me, even if the doors are locked, the AV equipment is still running somehow.
Yes, yes. And if you go ahead.
So it seems to me that it needs to be defined such that when you declare a building vacant, and that word vacant is defined, then the university says, okay, this is vacant. The following should be done in that particular building. Turn off all AV, something like that. So there is no question that, hey, the entire campus says, oh, this is vacant, and this is what is expected to be done.
Yes, now I understand what you're saying. Indeed, what we need is a protocol for building, for what should be switched off or what modifications to be made in the building when we know that it's unoccupied.
Right. Unless this is defined, then you have your own expectation. I have my own expectation. Then
yes, and the reason that's especially important is not only knowing what to switch off, but also to know what needs to be switched on when it becomes occupied again. And that is often more difficult and certainly more important to make sure that the services are restored. So I completely agree with you. We need to create that protocol.
Right, and it may affect the campus design guide.
Yes.
Right.
That's a very important point.
Well, thank you so much. We are just at the end. Perfect timing for the last question. And I wanted to thank Alan so much and all of you for joining us today. I hope we found it useful and informative. And we will work on getting the slides and the video posted here in case you want to follow up or use it for some future work of your own. Thanks so much, Alan.
Thank you very much.